Hmm. Good evening, everyone. Am I audible? Can someone please write in the chat if I'm audible?
Yes, ma'am.
Audible.
Right. So, yeah, I think we should start. I'm Liza. I am one of the assigned TAs of this course, Microprocessors and Microcontrollers, taught by Professor Shantanu Chattopadhyay, and I'll be taking your interactive session today. So we'll start with the summary of the lectures of this week. Uh, Please let me know if you have any doubts regarding the lectures and if I miss something, if I don't cover anything. Can you see my screen?
Yes,
Not
ma'am.
visible.
Not visible.
Yeah. Now it's visible. Yeah.
Okay, so I'll start with how Sir proceeded. Uh, First of all, what is the difference between microcontroller, microprocessor, and microcomputer, processor, and controller? So, do all of you understand what is the basic difference between the three of these definitions of three: microcomputer, microprocessor, and microcontroller? Is there any doubt? Okay, so let me first start with what they are. So, microcomputer is just a computer with memory and everything, but the main thing is its processing unit is a microprocessor. Okay, so any computer whose processing unit is a microprocessor is called a microcomputer. So that brings us to what is a microprocessor. Microprocessor is a processing device which takes in data, numbers, operates on them, gives output either to its output registers or some peripheral IO devices or peripheral memory. Right? That's a microprocessor. The peripheral devices or chips that are used to store the output are not part of microprocessor. That is the basic difference between microprocessor and a microcontroller. Microcontroller would have a microprocessor as well as the memory and IO chips embedded in on a single IC, right? That's the difference between microprocessor and microcontroller. I hope that is clear. So, should I move on? Okay. So, microprocessor normally recognizes and processes words, and words by definition in digital electronics is uh, array of 16 bits. A combination of 16 bits makes up a word, right? So next is microprocessor based system constitutes a microprocessor IO and memory that I have already. So IO and memory are not part of microprocessor. They are peripheral devices, right? So next thing is a memory map. Memory map of microprocessor 8085 was discussed by Sir in class, and I thought I would discuss that too. So, memory of microprocessor is divided into parts as told by Sir also. I'll move through this faster. So, it is divided into EEPROM, that is from 0000 to 3FFF. What is stored in this in these sections of the memories, EEPROM, RAM, RAM1, RAM2, will be discussed in subsequent lectures. So that is why it was not discussed here. So from 3FFF to 400 is blank. Then we have RAM1, RAM2, RAM3, and RAM4. Last bit of that is also blank. So RAM1 is from 400 to 5FFF. RAM2 is from 600 to 8FFF. RAM3 starts from 900 to AFFF, A3FFF. RAM4 starts from A4FF to F7FF. So this is the memory map. These are the addresses of different memory locations that are assigned as EEPROM, RAM1, RAM2, RAM3, and RAM4. Right? So yeah, moving on to the language that is used by 8085 is the assembly level language. As in, say this instruction INRA has the opcode INRA. I mean, we write it as INRA. Microprocessor doesn't recognize as INRA. INRA is fed into the microprocessor or programmed into the microprocessor as 3C. And 3C in hex code, as you know, is this is 3 and this is C. C is 12, right? So this is the opcode of INRA, this instruction, right? So next is 8085 architecture. Architecture was discussed by Sir, and I'll be explaining it in further slides also. So basically, 8085 is 8-bit general purpose microprocessor, and it can address up to 64K memory locations, and it has 40 pins and uses 3 megahertz clock, right? So pin diagram was also discussed by Sir in the class, and pop, the function of different pins can be also understood in subsequent lectures, right? So system bus. Microprocessor will have three kinds of buses. Buses can take in data, or since you know by the architecture, there are different segments in the microprocessor, right? So to fetch data, to fetch program, to decode it, to operate on that data, or put your output, whatever the data was operated on, and the result from that operation, to say transport all the data or the instructions can be done by these three buses: address bus, data bus, and control bus. Right. So, as the name suggests, address bus will get like fetch data, fetch hexadecimal numbers that represent the address of the memory or any location, right? So, address bus will is represented by A15 to AA and AD7 to AD0. So lower part or lower order address is taken or transported by these AD0 to AD7 lines, and higher order is transported by A15 to AA. So, as you must be seeing that this A15 to A8 is written as it is, but this the lower order address lines are written as AD7 to AD0, which means this address line is kind of special because it works as both data bus as well as the lower order address bus. So, yeah, we'll discuss this later. So data bus is, since the data is 8-bit, the microprocessor processes 8-bit data at some instant of time in one instruction. So it requires 8 lines, and these 8 lines are provided by these multi-purpose AD7 to AD0 lines. Next is control bus. Control bus, the function of control bus is to synchronize all the signals, right? So, control bus will dictate how and when the which data is going to be transferred to what part of the microprocessor, right? If some instruction is to be implemented, so control bus will tell the program counter to or the the microprocessor to get to the memory whose address is stored in program counter, right? Program counter, the control bus will dictate when the when the data is fetched from the address, what to do with that data. It will send it to the decoder, it will enable the decoder, and then it will be stored to then it will be sent to the accumulator for the operation to be for it to be operated on. So all of this is controlled by the control bus, right? Any question on system bus, or is it clear? Should I move on? I'll take that as a yes. All right, demuxing of the AD7 to AD0 lines. Do I need to explain this again? Can you please write yes or no in chat box? Okay. So, demuxing of AD7 to AD0 lines, first of all, you need to understand that AD7 to AD0 lines are they work as address line also and data line also, depending on some of the restrictions that or the way the microprocessor is built, right? We'll have some signal that will help the microprocessor, what do you say? Help it understand when to use it as address line and when to use it as a data line. Okay. So, so if I want to operate on some data, and data is going to come through this lines also, or this line only. Okay. So if I want to operate on a data, what do you think I need first? The data and the address of the data where it is stored, or the data only? Now, what would you require first? I mean, if you
Address of
want
the
to
data.
operate address of the data, right? So at the starting of the instruction, the microprocessor will do what? It will load the data address to the address lines. Okay, so we have address lines from A15 to A8 and AD7 to AD0, and our address is 16-bit. So it will require all the 16 lines, right? So what will the microprocessor do? The higher order address will be loaded to these lines, lower order will be loaded to the lower AD0, AD7 to AD0 lines, right? But what will it do? So we have, let me draw the diagram. I think it will help you understand that. Hmm. So let's say this is 8085. All right. This is the higher order bus, A15 to AA. Okay. And lower order bus is somewhere here. This is AD7 to AD0. Is it visible whatever I'm writing?
Yeah.
Okay. So, what does 8085 do to differentiate between whether to load data to this lower order bus or address? It uses ALE signal, that is address latch enable. Address latch enable signal is connected to a latch, right? This is latch, which will hold your lower order data. We have it will store A7 to A0. Okay, so what happens is, uh, first of all, 8085 will load all the data to all the address line, right? And during this addressing, huh, while it loads the data, ALE signal is also generated. ALE signal is generated as in when the data is loaded to the address bus, ALE will enable the latch. Okay. When it enables the latch, see this higher order address lines won't be disturbed anyhow during the whole of instruction, right? But this AD7 to AD0 will go on to the latch, load its data to the latch. Okay. When the ALE signal is generated, this lower order address, will go on to the latch. And since ALE signal is enabling the latch, do you know what latch is? I hope everyone knows. It's just a data storing, yes, component. So these 8 bits will be stored to onto the latch, loaded onto the latch. So this latch will contain A7 to A0. Once this address is loaded to the latch, this ALE signal will go to 0, which means it will no longer enable the latch. It has already the data A7 to A0, which signals 8085. Once ALE is off, it signals 8085 that this bus is now available for the data D7 to D0. So now the address is all on known, and the data bus is also available for fetching the data. This way, microprocessor manages to differentiate between address as well as the data. Is it understood now? And in the next instruction cycle, this when the next memory location's address will have to be loaded, the CLE signal will again be generated, and same process will happen again. Is it understood? Did I move on? You can explain again if you guys have doubt. Please let me know. Okay then. No. Priyanka, what is not understood? Can you please unmute yourself?
No, no, no. I have understood. No need to explain it again. That's
Okay.
why.
Okay. Sure.
I have a doubt in memory
Mhm.
folding actually.
Okay. Sure. We can discuss it in end if you
Yeah, yeah,
will
yeah.
be available. Yeah. Okay.
Mhm.
Mm, all right. So next point is memory register. I think it is easy to understand what a or first of all, we need to understand what are the different addressing modes of the before knowing what memory register is. So 8085 has basically five kinds of addressing modes. Okay. So I am unable to erase this. So there are five kinds of addressing modes. And I'll be discussing them one by one. Okay. So first of the addressing mode is the immediate addressing mode. First is immediate addressing mode. So in this kind of addressing, source operand is always the data. As in, if you know basic structure of instruction, as we discussed last time, so instruction has two parts: opcode and operand. So, for example, if I take this instruction, or any instruction, um, move MB. In this instruction, this MOV is the opcode and these are the operands, right? The opcode will tell microprocessor what operation is to be done, and operands will be just telling it that or indicating what data that operation has to be done on. Okay, so in immediate addressing mode, the operand is always the data, right? So, which means, say, if I have instruction MVI B45. Now, this instruction is telling the microprocessor that move immediately the 45, this data 45 to B. What is it telling? That now, if you can see, the operand is directly a number. We are not referencing to the data through a register or anything, right? We are directly telling the microprocessor that this is the number loaded to some register. It could have been another register also. Okay, so this is the first kind of immediate addressing mode. Second is register addressing mode. Addressing mode. So in this kind of addressing mode, the data that is to be operated on is available in some register. Like, there are how many general purpose registers? Seven general purpose registers are present in microprocessor, right? A, B, C, D, E, H, and L, right? So in register addressing mode, uh, the data that is to be operated on is present in one of these registers. For example, if I write move A B, So what is this instruction telling the microprocessor? That move the contents of uh, B register to A. That A will get the contents of B, right? So you are not using a directly a number. You are referencing to a register that contains the number that you want the operation to be done. Easy. So next kind of addressing mode is the direct addressing mode. Now, in direct addressing mode, the data that is to be operated on is stored at the address that is given in the operand as the operand in instruction. Okay. So, for example, uh, LDA 2050H. So this instruction is telling the microprocessor to load the content of memory location which is given as operand. Now this is the memory location and the microprocessor is told to go to this memory location. Let's say this is the memory. This is 2050H, 2051H. Microprocessor UP has to go to 2050H, see what all data is there, and load it to accumulator. Understood? So A will get the data of location, data of location that is given as object. Okay. This was direct addressing mode. Next is the register indirect addressing mode. Both is register indirect addressing mode. So in this kind of addressing mode, data that is to be operated on is present at the location indicated or pointed by the register pair. It is similar to the direct addressing mode only, but in direct addressing mode, what were you doing? You said LDA 2050H. You were giving the address, like you were giving the address of the location yourself. In register indirect addressing mode, what do you do? For example, like this move MB. Now, you are asking the microprocessor to move the contents of B to the address that is pointed by M. Now, M here can be any register pair. Registers can be paired, like H and L can be paired, B and C can be paired, D and E can be paired. So so M corresponds to the HL pair. B and C can be mentioned separately. You can write them differently. But if in instruction M is given, it is directly understood by microprocessor that the location address is given in the or the address of the location is stored in the HL pair. Okay, so this instruction, what is it telling? That move the contents of V to the location pointed by the content of HL pair. Is it understood?
Yeah.
Can someone please tell me if this one is clear?
Yes.
Uh, but here this move is similar, move m comma b is similar to the register addressing mode instruction, right? For example, move a comma b. So here in this case only this is the m which is differentiating from both the instructions.
Yes, yes. M will always be M will always mean the HL pair. That is why it's given a different name, memory register. I wrote it before the addressing mode, but first we need to understand what is the addressing mode. Then you need to understand that this is this very special kind of register pair, and it has a name. And wherever M is given, it means the HL pair is referred.
Oh, okay, thanks.
Anything else? Similar, we can have more examples like if I say add M, what does this imply? No, it doesn't imply, but add M is an instruction which tells the microprocessor to add the content stored or data stored, uh, add location pointed by M, which is HL pair, to data in A. Is it clear? Similarly, we could have INRM, which means increment the data that is stored at the location pointed by the HL pair or memory register and by 1. This instruction will increment the data which is at, say, M contains 2050. So, and this is the 2050 and here is some data. So this instruction will do what? It will increment this data by 1. Like if the data was 44, it will increment it to 45. Yeah. So yeah. After this, last one is the implied addressing mode. With this implied addressing mode. So implied, as name suggests, the function of the instruction is implied. You need not to mention the operand, right? For example, we have CMA, which says, which means or translates to complement the content of A, accumulated, right? If you have some data stored in A register, this instruction will just do a ones complement on this data. Okay, so no operand is required. Like before, we had what was, if I say INR M, we required operand, right? So in these kind of implied addressing modes, the operand is not required. The operation is understood, and the operand is understood whatever to do, like what data to operate on. And these RLC, RAC, RRC are also examples of these only. Should I explain these rotation instructions? Please write yes or no, or else I won't. Yes. Okay. So these are also implied addressing examples of implied addressing mode. So what does this mean? RLC, let's take first. So RLC means to rotate the content of A, rotate the content of A right to the right by 1 bit. Okay. So how does this work? Let's say we have 8-bit data. Okay. This is the D0. This is D7. And RLC is telling the microprocessor to rotate the content of A to right by 1 bit. So right means this bit will move to this one. RLC is right. RLC is left. I'm sorry. Well, let's do RRC. I'm sorry, I just got confused. So yeah, RRC means rotate the content of A to right by 1 bit. Okay. So right means this will move here. This bit will move. D7 will move to D6. D6 will go to D5. Similarly, all of these will move. So where will this D0 go? All of the bits are shifted. D7 has gone to D6 and D7 is empty right now. And D0 has to go somewhere.
The carry flag as well
Yes.
as D7.
Yes. So this D0 here will have carry flag, the bit in carry flag, as well as this D0 will go to D7. Understood? Now to differentiate it from the RRR, let's do RAR once and then RLC and RAL are similar, right? So if we again have this 8-bit data, this is D7, this is D0, and it is again telling it to move to the right by 1 bit. So D7 goes here. Similar, where will D0 go now? And what will D7 get?
Now D0 will go to carry flag and the value of the carry will go to D7.
Yes, exactly. So D0 goes to carry flag. Carry flag goes to D7. I think everyone understands this. Someone asked me to explain it. Is this clear? Similar for RLC and RAL also. RAL will move the D7 to in RAL. D7 will go to carry flag and carry flag will go to D0. In RLC, D7 will go to both carry flag and D0. Carry flag and D0. Is it understood? Okay. Okay, so these were some of the implied instructions. Next is arithmetic operations. I think arithmetic operations must also be clear to you. Very easy. Add, subtract, or not all. Okay, so for the instructions like add, ADI, subtract SUI. The destination is always accumulator. Okay. So whatever be the instruction, there will be some operand given in ADI, ADD, and this result of that operation will always go to accumulator, right? So similar to using the memory register also, we could have add M. I think we just uh, discussed this example. Add M will do what? Add M will add the let's say M points to some location, and the microprocessor will fetch the data from that location, add it to A. Let's say we'll call this is some data that it fetched from that memory location pointed by M, and the result will be stored in accumulator. Okay, similar for subtract M also. Yeah, so these are the arithmetic operation. Then we have logic operations. So logic operations, as we know, are AND, OR, XOR, XNOR, NOR. So similar to those only, we can AND to accumulator and immediate. So all of the opcodes which contain I, that is for immediate addressing mode. Okay, as we discussed previously. And to A and immediate, or to A or immediate, then XOR immediate. These are the logic operations. Now, once you start programming, you will be more familiar with their usage. Okay, and these rotating instructions we have already discussed. Uh, is everything clear on this slide? If anyone has some doubt, please ask now, or I'll move on to the next one.
Ma'am,
Yeah,
ma'am, please repeat the RAL and RLC.
RAL and
RLC.
okay. So, did you understand the RRC and RAR?
Yes, ma'am.
Okay. So, in RLC, let's say you
Ma'am,
have
can you repeat RLC once again?
RALC. Which one? RLC or
RLC.
RLC? I'm doing that only. Let's say this is your D0 bit, D7, right? So, what will RLC do? Rotate the contents of this is accumulator, right? So rotate the contents of accumulator to left by 1 bit, right? So D0 will go to D1, D1 will go to D2, and similarly, the question will arise, where will D7 go? Now for RRC, I think I should draw these simultaneously. D0, D7. What was happening in RRC? The bits were moving to
Yes, ma'am.
right? So where did D0 go? There is
D0
the
goes
carry
to
flag.
D7.
What? Can you please repeat? Where did D0 go? In this is RRC. This is RLC. I'm doing RLC here. Huh. So in RRC, D0 went to carry flag as well as
D7.
D7, right? Because D7 had the empty space, it needed some bit, some information, some data, right? So, and here, if you see in RLC, which bit is empty now, which has space to get more data? See, D0 went to D1, D1 goes to D2, D2 goes to D3, and so on. D6 goes to D7. So all of these bits have some data. D0 doesn't have anything. It just gave away, it didn't receive anything until now. Right? Just as here, D7 was empty and it didn't have anything. So D7 required some information, some bit, and D0 didn't know where to send it, right? So D0 was told to send its data to carry flag as well as D7. Here, opposite is happening. D0 is empty and D7 doesn't know where to send the data, right? So D7 will send it to carry flag as well as D0. It's a similar process, only one is rightwards and one is leftwards. And whichever bit doesn't know where to send the data, it has to see if it has to load the data to carry flag or not. Yeah.
Yes, ma'am.
Similar for RAL. Do I need to, or will you guys work with me for RAL? You can do RAL and RAR simultaneously. Let's say this is for RAL, RAR. So what was happening in RAR? Can someone please write or unmute themselves?
In RAR, ma'am, D7 goes to D6 and D6 goes to D5, D5 goes to D4 up to D1 goes to D0 and D0
Yes.
goes to carry flag
Hmm.
and carry flag goes to D7.
And carry flag goes to D7, right?
Yes.
This was understood. So what will happen in RAL? This is D7, this is D0. Everything will move leftwards, goes to D1, D2, D3, D4, D5, D6, D7. And here is the carry flag. Where will D7 go? Both CF and D0 or just CF or just D0?
D0. Sorry, D7.
My question is where will D7 go?
Carry
D7
flag,
has
ma'am,
already.
also carry flag and also D0.
No, but see, this is parallel to RAR and like it is comparable to RAR only. Here you see D0 was going to carry flag and carry flag is then going to
Goes.
D7.
Yes, ma'am. In
Right?
RAL, ma'am, the D7 goes to carry flag and carry flag goes to D0.
Yes. So this goes to carry flag and carry flag goes to D0. Is it understood?
Yes, ma'am.
Anyone else who has not understood this? So this RLC is rotate left with carry. RAL is just rotate left in a very nice symmetry. D7 goes to CF, CF goes to D0, and all of the bits are in RLC. What was happening? This D7 had to go to carry flag as well as D0. This RLC full form is rotate left with carry. It means it has to go to carry as well as to D0. Similar for RRC, rotate right with carry. I think if you remember the full form, then it'll be a little
May
easier
I
to,
interrupt, ma'am?
yeah, yeah.
I think RLC is rotate accumulator left only. Where C is present, there no use of you know carry flag in that instruction.
No, RLC is with carry. That is why C is present. For the accumulator, where C is not uh, like for a very nice sequence, here RAL, like you see here, there is C
No,
not
in
present.
RAL rotate accumulator left through carry. Through carry. In
Yes.
RAL and
Huh.
RAR through carry.
Yes.
There where
Yes.
C is not present in those instructions, it is through carry. And where C is
Mhm.
present in the instructions, they are only rotate accumulator right or left.
Yes, but the content goes to
Yeah,
both
yeah. But
carry
the
flag
yeah,
as
yeah,
well
yeah.
as,
No, no.
yeah.
I'm only telling the full form.
Oh, oh, thanks for that. I couldn't see who it was. Okay, should I move on?
Yeah.
Okay, so next is I think architecture was discussed in like fairly in the lectures, but I just want to see if yeah, we'll just go through what is the purpose of all of these like basic components of the microprocessor, right? So in architecture, we'll see that there are basically seven general purpose registers in 8085, right? So these general purpose registers are seven. We have seven general purpose registers, namely A, B, C, D, E, H, and L, right?
Ma'am,
Ma'am,
Yes.
is A
general
a
purpose
general
register
purpose
is only
register?
6.
Yeah.
No,
A
A
is
is
not,
also
ma'am.
considered. A is also considered
A,
as general purpose.
Okay.
I think Sir said six. No,
Yes,
I
ma'am.
don't
Only sir
remember.
said 6 general purpose
yeah.
register.
Okay,
B,
so
C,
maybe
D,
you
E,
should follow
H,
him.
and L.
Yeah. Okay. Otherwise, A is also considered, but for the
A is
time being,
considered
let's
a
say.
special purpose, that as I told.
Oh, okay, it's okay. So, so these are the seven general purpose registers. Then we have special purpose registers, like program counter and stack pointer. So what are the do you say? It is the job of program counter. Come on, faster in chat. I think everybody has
It
understood
can
the architecture.
hold the address of the next instruction to be fetched.
Yes, perfect. So program counter, like everyone will know it contains the address, but it needs to be understood that it will hold the address of the next instruction, not the current instruction, right? Once the address is used to, decode or get the instruction, the program counter is incremented so that it points to the next instruction. And when microprocessor is ready to implement the next instruction, it doesn't have to wait for the program counter to increment to get to the next address, right? Next is the stack pointer. What is the purpose of stack pointer? Yes, anyone? Should I explain?
Yeah.
Okay. Okay. So,
It is used
stack
to
pointer.
memory.
Yeah. Yes. Yeah. Please go on.
Madam, stack pointer will hold the address when we
Mhm.
execute any loop. After
When we
finishing that loop content, it will go back to that address, previous address.
Okay, so basically, stack pointer will point to the address of the top of the stack. You know what a stack is, right?
Yes, yes, 07H.
Yes. So stack is just, yes. So stack is just some memory locations reserved for it to be uh what do you say? Push in or pop out instructions. So stack will be a set of locations, and the stack pointer will point to the topmost address of the stack. Like, you know how stack is filled, right? First, first in. Okay, so stack works as first in,
First
last
in,
in,
first
first
in.
out,
Yes.
last in, first out, right? So last in, first out. So if s- some data is loaded onto the stack, say data is loaded onto the stack, and up until here stack is filled. So the data will go to which address? Let's say this is 1, 2, 3, 4. Which location will the data will load to? 1, 2, 3, or 4?
Where is the stack pointer now?
I am
Ma'am?
saying the stack is filled up until this location. This is 5. And
Okay.
below are more. All of these
Hmm.
are filled. Huh.
Mm-hmm.
So where will the
The
data now go to?
uh, 4, location 4.
4. Okay. Let's say I fill this location by 4. Let's say the data is 4C. Okay. And now I want to load data to 2. Where will the data go?
3,
3.
location
3.
3.
Yeah. 2 H will go to 3. Now let's say I want to get back the data from memory.
First 2 to
And I
move
22
want,
H
here.
written.
yeah, one by one. I want to get back the data, but I want this data at location 4. Can I get that data
No,
in
ma'am.
one instruction?
Yeah, if I use pop, then it will get back the data as that sequence only. Last in, first out.
Yes, last in, first out, but I want to get 4C first. Is that possible?
Yeah, no, no, no,
No, ma'am.
not possible.
No, right? So the stack pointer will keep pointing on to the top of the stack. Right now, the top of stack is 20, the location which is containing 22H, right? So if I want to retrieve the data, I'll have to implement the instruction pop out, right? But the pop out will give me the data to which data of the location which is pointed by stack pointer. So stack pointer right now is pointing to 3, so it will pop out 22H only. Right? After I have popped out this data, this location will be empty, and the stack pointer will then point to 4, this location 4, and then I can, if I want 4C, I'll have to pop out again. Understood?
Yes, ma'am.
So
Yes. Ma'am.
these are this is how stack pointer works. Now, next is ALU, arithmetic logic unit. So all of the arithmetic operations will be done in arithmetic logic unit. So actually in this figure, it is drawn like this only. But generally, arithmetic logic unit is drawn like this. You must have seen it in some architecture diagrams, right? So this is ALU. What does, why generally this shape is used for ALU? For any other arithmetic operation, you'll require two operands, right? So if one operand goes here, another goes here, the output will be one, and that will come out this way. This is just to remind yourself that which direction the arrows go, right? So one input, another from accumulator, and it goes out. The other ALU has to go to. I think one bus is missing here. Yeah, bad diagram. Okay, so ALU will give the data to this, and from here it will go to accumulator or wherever you want to store the data. Right? So generally this shape is used. Here it is square, which is okay if you remember the arrows. So yeah, this is arithmetic logic unit. Then next thing is the flag register. Flag register was also discussed by Sir orally in class. Do you want me to go through it again? Is flag register clear?
Yes, ma'am.
So I need not to do that, right? So next is the system bus. System buses we also did in previous slides. There are three kinds of system buses: address bus, data bus, and control bus. Right. So here is your address bus. Right. This is your data bus, and this is your control bus. So this control circuit will control how the instruction is decoded and where it is stored and all of this, right? So I think we have discussed this also. So non-programmable registers are is I don't remember if this was discussed in class. I think it was discussed. Yeah, so the instruction register and instruction decoder are the non-programmable registers. We cannot change how they work. So they are destined to do something. And, so the instruction register will hold the instruction. It will know what instruction is fed in, what operation is to be done on the data, and then instruction register gets the instruction. It sends the instruction to decoder. Decoder decodes what instruction, what operation is to be done, and then is sent to control circuit, and then control circuit in directs accumulator, ALU, or whatever operation that is to be done, and in that way the instruction is executed. Right? Any doubt about the non-programmable registers or the architecture in general? Think not.
No, ma'am.
Okay. So let's move on to the problems. Yes, so I think the problems this week are pretty easy, nothing to be solved for. You just need to know how microprocessor works and what all are the function of the different
Oh,
units in the microprocessor. So I would like if you all write your answers in the chat and we can see if they are correct, right? Please excuse me for a moment. Mm.
Ma'am, answer is B.
Yes. Can you see me now? Okay, so yeah, some people have worked out. So the question is, which of the following statement is correct? Microprocessor, everyone is saying B, let's say. Processor contains ALU registers and control units. Correct. So why are all the other options wrong? It does not contain memory because if it had contained the memory, it would be microcontroller and not microprocessor. And it has registers, so C is obviously wrong and D is correct. So B is the correct answer. So next question. In 8085, which of the following cannot be done by single instruction? Adding two registers, multiplication by powers of 2, division of powers by 2, division by powers of 2, and or none of the other, or everything can be done. Please write your answers.
Multiplication and division both.
Cannot be done.
Yeah.
Anyone else? Someone is saying D. Please write your answers. Should I wait or move on? Alright. So, yes, the answer is D. You can do multiplication, you can do division, and obviously add two registers. So, I think with the lack of programming, that is That is why you're saying multiplication or division cannot be done. Once you start programming, you'll understand what all can be done and cannot be done. So, next question. How many pins does 8085 have?
40.
Answer
40.
B, ma'am.
B. Everyone.
Yes, ma'am.
Yeah.
B is correct answer. Next question. Size of instruction
1
add
byte.
M.
A.
Anyone else? Hmm. Even if you don't speak, you can write it in chat. If anyone saying B, 2 bytes, or does it depend on value of HL pair? Anyone is saying B.
A, ma'am.
Two people are saying B. Okay, so answer is A. The instruction size is 1 byte only. 1 byte, right? It just refers to the M is HL pair, we know, but it points to the address where from where the data is to be retrieved. Okay. Answer is
Say the size of instruction does add also not include here.
sorry. Can you
I
please
mean, when
repeat?
we say the size, I mean,
Uh-huh.
when we say the size of the instruction, should we not include the opcode also?
No, it's okay. So opcode is the instruction. Operand is different. Like this is a mnemonic for, I think for add is mnemonic for CC.
Opcode and operand together called the mnemonic actually.
No, actually this is the mnemonic. Opcode has a mnemonic, right? Wait,
No, ma'am. Actually, opcode and operand together called mnemonic, and this whole mnemonic has only one hex code. So that's why it's 1 byte. And
yes,
the length of that is 1 byte. And there is no
yes,
data 8 bit or 16 bit after following this instruction. That's why it is 1 byte.
yes. That is what I'm saying. That M is referring to the M might have the address of the location from where data is to be retrieved, because some people were saying the size is 2 bytes. So they might be confused from because M is used here. So M is only referring to the HL pair or the register from where the address of the location where from where the data to be retrieved is stored. So it cannot be 2 bytes. I think someone was saying B, so that is why I was telling them. Is it clear now?
The M register will refer to the HL register as a whole or H and L separately.
So M is the let's say it's the indication of the HL pair together, right? So when you want to refer to the address or point to the address which is stored in these, so H is 8 bits, L is 8 bits. Together they make 16 bits, and since together as a pair they can refer to an address because addresses are 16 bits. we refer this HL as M. So it will have some number, say 0, 1, 1, something. L will have something, and together, let's say they have 2050 is stored. 20 is stored in H and 50 is stored in L. Together, when this kind of instruction is used, add M, that will say that you add the contents of the location whose address is stored in HL. You can write this if you are not understanding. This means add the content at which is or which is present at the location whose address is stored in HL pair. Okay, and add the content to add this to accumulator. This is what this instruction means. Is it clear?
Yeah, yes, ma'am.
So yeah, the answer is A. Let's move to next question. Hmm. So yeah, what is the clock speed of
D.
8085?
D.
Everyone clear on this? I think D. There's nothing to be wrong about this one. Next question. So identify the addressing mode of 8085 microprocessor in following instructions. So instruction is
Immediate.
given immediate.
A.
You are saying immediate. Everybody else, please write in the chat. This is easy. Please write. It is immediate. And this is like MBI in opcode is very indicative of what the addressing mode is. So this is immediate. Right? Next question. ALE signal is made high in 8085 to do what?
A, I think.
Please write everyone. To enable the data bus, to latch data from data bus, to disable data bus, or to achieve all of the functions listed. All right, so as we discussed, ALE signal is made high to enable the data bus to be used as low order address bus after the address is latched onto the latch. Right? So answer will be A. Everyone clear on this?
Yes, ma'am.
Okay. So yeah, next one. So 8085 has which of these combination
B.
of address bus and
B.
T? Anyone else saying differently? Yes, so this is correct. I think there's no doubt about this. 8-bit data bus and 16-bit address bus. Right. What is the meaning of instruction that B? I don't know if this was discussed in this was or not, but does anyone know what is that B?
D.
Should I wait or
Answer D, ma'am.
D? Everybody else? No, ma'am. D. Yes, please write. Go on. Yes, so answer is D. That B means to add the register pair HL with the register pair BC. The content of HL will be added to content of register pair BC. So D is the correct answer. Someone said C, I think. Yeah, it's not C.
That is DA, I think, in C.
Yeah, yes. So I hope this is clear. Let's move on to the next question. Identify the correct addressing mode for the following instruction. ADCM. Which addressing mode does this refer to? M is used here. ADC. Please write your answers. Yes, pretty much everyone gets this. Since M is used, it's indirect addressing mode. D is the correct answer. Next one. INX B instruction does what?
C.
Does it increment the contents of register B by 1, increment contents of C by 1, increment contents of register pair BC by 1, or content of C is incremented but content of B is unchanged?
Both the contents are incremented by 1.
Yes. So the contents of register pair together BC is incremented by 1. INXP instruction. C is the correct answer. Right? Next question. What does CMA instruction do? Decrement the contents of the accumulator, performs one complement of accumulator's content,
B.
perform two's complement, or increment the content of accumulator. CMA,
Complement.
one's complement. We discussed this. And can anyone tell me which addressing mode this is? Implied, since there is no operand. Next one. What does the normal add instruction do?
Number C. Add immediate to accumulator.
Think again. A or B?
B, I think. B. Register or memory to accumulator.
And why not C?
No, ADI will be for that, no? Add
Yes.
immediate.
Yes. So please take care. So ADI will be for the immediate addition, and in immediate addressing mode, we also have operand as number, right?
Yeah.
So correct answer is
B.
B. So B is the correct answer, right? Yeah. Next question. Accumulator is how many bit register?
8-bit.
Everyone clear? Is it 16 bit? Someone is saying 16. See, accumulator is 8-bit register. All the other registers which are specific, which are 16-bit are mentioned explicitly. Accumulator B, C, D, E, H, and L are all 8-bit registers. Okay, so C is the correct answer. Next is uh, 8085 that doubles the value of accumulator is
Add A.
known as yes. So add A will do what? Add A will add the content of A to A and store it in A. So actually A will get twice of what it had before. Right? So yeah, that's it for today's questions. If you guys have any other doubts, I think someone was asking about memory folding. I can discuss that. And last time someone was asking about doing the full subtractor using two half subtractors. So you can do that also if you guys want. So yeah, who had the doubt about memory folding
Me,
and
ma'am.
what was the doubt? Yeah, please. What's the doubt?
So, in case of memory folding, actually, that conception that how many bits we are using, how we are selecting that chips. So that is, I have that confusion. Chip
So are we
selection.
selecting chips or how is memory folding happen?
So how we are selecting the chips for that, we are repeating using that those memories. Those are for the memory folding. Yeah,
Yes.
that I
Huh.
have confusion. I have not cleared that part.
Okay. So how should we do it?
Yeah.
So do you have doubt that how chip selection is done? Is that clear?
In case of chip selection, yeah, yeah, you please repeat from that chip selection part.
Should we do that? What do I say? Last time's question in which we configured the memory, RAM, RAM memory.
Yeah, one example by one small example if possible.
Huh. So let me just load on to the previous week's slides. Just give me a minute. Okay.
Okay.
Mm. Yes. So, can you see my screen?
Yeah, yeah, it's visible.
Oh, just a minute. Okay. So, did you have problem in solving this question, or did you understand it?
Yeah, I understand this.
Okay.
But
So, if you remember, the answer was this, right? I need not to redo how we got this answer.
no,
If,
no, no.
yeah.
It's clear. Yeah.
So, so
Ma'am, I have
the
doubt, ma'am.
yes.
Ma'am, can you once again shortly tell how to derive that answer, ma'am? I have doubt on this.
Okay. Okay. I can do that.
Briefly, can you
Okay.
explain?
Yeah.
Briefly explain, ma'am.
I'll do that. So, the question is, first of all, understand what the question is. If chip selectors A15 prime, A14, A13 prime is used to select the chip of 4K RAM in 8085, then what will be the memory range? This is the question, right? So, first of all, we need to know I I hope everyone knows by now that 8085 has 16-bit address lines, right? So we'll have 1, 3, 4, 8, 12, and 16. So this is A15, this is A0, right? So, uh, okay. So, for the 4K RAM, first of all, we need to know how many addresses will be there in a 4K RAM, right? 4K means how many number of memory locations will be there in this RAM? Can anyone tell me? 12-bit, right? Because 2 to the power 12 is 4096, which means 4K, which is our chip requirement. So 4K RAM will need 12 lines for each of its memories to be addressed, right? It won't need more. Is that part clear? Uh, who was
Yes, ma'am.
asking for? Yeah, I don't know your name. Someone who has doubt in memory folding also, please understand this. So, 4K RAM will require, this is A11, this is A12, right? So, these 12 lines are all required for this RAM to be addressed, right? These four are not
Yes.
required. This part is clear? So, all of these A0 to A11 can go from 0000 to FFF. Let's leave this one blank for now. Do you know how this zero is coming from? Like this zero is actually 0000 for A0 to A3.
Yeah.
This one is clear, right? So all of these lines can go from A0 to A11 can go from 0000 to FFF for all of the 4K RAM's memory to be addressed, right? So these four are left, and we need to know what should we do with these four lines, right? So in question, it is given, and it is our choice what lines to make chip select. Like it is manufacturer's choice, not our, but it is still like he can choose. A manufacturer can choose what chip select lines he wants for his this RAM, right?
Okay.
So, huh. So this chip select is given. Let's say this chip select let's take this example only, then I'll take another example also. So chip select means This signal is when, and one more thing. So if this is RAM, and this is chip select, this is your signal coming from 8085. Okay, chip select will come from 8085. So, first of all, we need to know whether this chip select is enable high, enable low. Since it's not given, we'll take it as it is. So, chip select is A15
Active
prime,
low.
A15 prime, A14, and A13 prime. Okay, which means we are fixing the values of these three lines as given by chip select, because if the value of A13, 14, and 15 is any different from the values specified as chip select, this RAM, this 4K RAM will not be selected by the 8085 for any read or write operation.
Okay.
To access the memory locations of this RAM, the 80, I'm sorry, I wrote 805. 8085 has to enable this chip first, so as to for it to know which peripheral device or which peripheral chip it has to see. Here in this question, it's given this one RAM. There might be some other peripheral devices also that this 805 can store data on. So to differentiate between which chip is to be selected, different chip select signals are used for different, like if this chip select is for this 4K RAM, if this is also say 4K RAM, this chip select of the second 4K RAM will be different from this. Because if chip select of second RAM is also same, then 8085 won't know where to send data or where to get data from. That is why I said all of the chips have their own chip selects, and that is our choice what chip select we're going to use, or the manufacturer. Okay. And once you
Yeah.
know the chip select of the RAM, you fix those lines as the chip select values. Like one A15 prime should be A15 prime means it should be low. A14 means it should be 14 line will be high, and A13
Low.
prime means this should be low, right? So we are fixing the values of this A15, A14. We are fixing the values of 0, 1, 0 on these three lines. Understood?
Yes.
Yes.
Yes, ma'am.
And A0 to A11 we have already discussed because we need all of the memory range of this 4K RAM. They'll go from 000 to FFF. Right? Which leaves us with A12, right? So there's nothing specified about A12. If it was given, we had chosen that, right? But since it's not given, what values can A12 have?
Maybe zero, maybe one.
Maybe 0, maybe 1, right? It can have 0 as well as 1, right? So let's say uh, for uh, when A12 is 0, what will be the value of this whole 16 bits? This first one will be 0100,
Then all the zeros.
then all the zeros all the way until A0, right?
Yeah.
And since for this case, this is case 1, A12 is 0. This will remain as it is because
All the ones. Yeah.
these are
For all
already
the
fixed, right? And these will be all ones.
ones.
because this can change. We are fixing these ones.
Mm.
This is already fixed by chip select, and we are considering the case of A12 to be 0. So what addresses do we get from here? These are all from 0000 to FFF,
Yeah.
and these give us 4.
4. Yeah. So
0100 is 4.
4000 to 4FFF.
Yes. Now this is for case 1 where A12 was 0, right?
Yeah. Yeah. Yeah.
Now let's
If
take case 2.
812. Yeah.
Huh. When
Where A12 is
A12,
1.
A12 will be 1, which
Yeah.
means A12 is this bit.
Yeah.
So we will have
0101.
0101,
Yeah.
000
Mm.
until 0101,
All
111.
the F. All the 1. Yeah.
Yes, right. So this will give us what?
5. All the 5.
5
4 3 zeros.
and
And
5,
5 triple F.
right?
Yeah.
Which
Yeah. Right.
means
Mm.
for the same memory locations
Mm.
that this 4K RAM, 4K RAM cannot have more than these locations, right? It can go from 000 to FFF only. The same
Yes.
memory locations will be addressed or indicated to depending on value of A12.
Yes. Mm.
Yes, which means same memory locations are like we could have chosen a larger RAM, or if there was a larger chip with more memory, uh, and if that chip required 13 bits, so we could have addressed more memory locations
Yeah. Of
using this
course.
A12,
Yeah.
right?
Yeah. Mm.
So this is the concept of memory folding, that for same lines, depending on value of A12, you are like, if memory location is say 101, right? For 4101 or address also, you will go to this location, and 5101 you'll go again to this location, because our range is from this, from range is this as well as this,
Yeah.
depending on value of like value of A12 doesn't matter, but for both of these addresses, uh, combination of 16 bits, it will go to same memory location. Second,
Yeah. Yeah. Understood.
so that was the concept of memory
Memory
folding.
folding.
Yeah. Is it clear to everyone else?
Yes, ma'am.
Clear. So yeah. So I think we can wrap our session here. Since there was no solving required in today's session, it was easier and shorter. So yeah, thanks everyone for joining. I'll see you next week. And please let me know if there are any questions. And you can ask your question in the course forum also. And you can mention if you have any doubts regarding this session. You can explicitly mention that this is the doubt from this session. And I was late in uploading last week's session, but it has been uploaded. You can check in the spreadsheet link that has been given to you. And I'm hoping to upload this time soon also. Okay, so thanks everyone. Good night.
Good night.